On the morning of November 25th, 2020, something failed across AWS's largest data center region, and within 2 hours, Netflix had slowed, Adobe's creative tools had gone dark, and the error dashboards of companies across the internet had lit up simultaneously. AWS published its incident report 2 days later. The cause was not a power failure, not a software bug, not a cyber attack. A number had been reached. Most outages follow a recognizable pattern. Something that was working stops working. A bad deployment, a hardware failure, a configuration error. You look for what broke, you find it, you fix it. A limit failure is different, and it is disorienting in a specific way. The code is fine, the infrastructure is running, nothing has corrupted. The system has reached the maximum of something: requests per second, concurrent connections, API calls per hour, and it is now refusing to accept more. From the outside, a limit failure is indistinguishable from a catastrophic breakdown, but the cause and the path back are completely different. For most people first encountering cloud computing, this feels like a contradiction. You have heard the cloud described as vast, elastic, theoretically unlimited. The marketing materials do not lead with ceilings. So the first time an application hits one, the instinct is to look for what broke, and that search leads nowhere because nothing broke. The limit was reached, that is all. For engineers who have spent years building on cloud platforms, limit failures are a constant, low-grade hazard. Not because the limits are unreasonable, they usually are not, but because they are invisible until the precise moment they apply. Before naming what these constraints are, it helps to think about a more familiar version of the same idea. Above the entrance to every restaurant and bar with a license to operate, there is a maximum occupancy number. The building could, physically, hold more people. The walls are not at their structural limit. There is floor space going unused. But the fire marshal has looked at the exits, calculated how many people can be safely evacuated in an emergency, assessed how much load the ventilation system can carry, and set a number. When the venue reaches that number, the door staff turns people away, not because anything is broken, not because the establishment has failed, because a designed limit has been reached. The person turned away at the door does not see any of that. They know only that they cannot enter. From the outside, a venue that has hit its maximum occupancy looks identical to a venue that has closed for repairs. This is the experience of hitting a cloud limit. The service looks the same from the outside, whether it has crashed or hit a ceiling. You receive an error, the request fails. But what caused it and what resolves it are completely different problems. The analogy holds up to a point worth naming explicitly. A restaurant's occupancy limit is set by a fire marshal and cannot be renegotiated on a Friday night. Cloud limits are frequently adjustable. You contact the provider, explain your use case, and request an increase. Many limits go up willingly. This process is built in. Some limits cannot be raised at all. The distinction matters, and we will come back to it, but the structural idea holds. These are designed ceilings, not accidents. Cloud limits are constraints that a provider places on how much of any given resource a single customer can consume within a given time period. They exist for two related reasons. The first is infrastructure protection. Cloud platforms are shared environments. When you use AWS or Google Cloud or Azure, you are using physical infrastructure that thousands of other customers are using simultaneously. If one account could consume resources without any ceiling, it could, under the right conditions, starve the infrastructure that everyone else depends on. Limits are the mechanism that prevents any single customer from doing this, regardless of how much they are willing to pay. The second reason is operational predictability. A provider cannot reliably commit to the performance of its platform if it cannot predict the load on it. Limits allow the provider to make capacity guarantees, to say, with confidence, that the service will behave a certain way, because they can model the maximum demand any single customer is able to place on any part of the system. Every cloud service you interact with has limits attached to it. The number of API requests you can make per second, the number of virtual machines you can run at once, the volume of data you can store in a single location, the number of database connections that can be open at the same time. Most of the time, you are nowhere near these ceilings and they are invisible to you. The limits exist. At your current scale, they do not apply. The moment they do apply, the experience shifts completely. Requests that were succeeding moments ago begin returning errors. Systems that depend on those requests start to fail. And if the limit you have hit is one that other parts of your architecture also rely on, the failure spreads in ways that can look, from the outside, like a total breakdown. This is exactly what happened in November 2020. AWS hit an operating limit inside a service called Kinesis, a data streaming platform most people outside AWS operations have never heard of. The reason it mattered was that AWS's own internal infrastructure uses Kinesis. When Kinesis hit its ceiling, the services that depend on it, authentication systems, monitoring tools, certificate management, began to fail. The services that depend on those services failed next. One limit, reached once, propagated outward across the region. There is a temptation, when you learn about cloud limits for the first time, to treat them as a design flaw, something to engineer around, or to pressure the provider into removing. That framing misses something important. The limits that can be raised are raised routinely. A team demonstrates growth, explains a legitimate use case, and the ceiling goes up. This is expected. Providers build the increase process directly into their operations because they anticipate it will be used. The limits that cannot be raised represent real constraints in how distributed systems work. No amount of money buys freedom from the time it takes to move data across a physical network, from the physics of reaching agreement between machines in different locations, from the hard boundaries of what hardware can sustain under load. Some ceilings are genuinely ceilings. The honest complication is not that limits exist. It is that they are invisible before they become relevant. Most providers document their limits, and the numbers are published. But documentation assumes you know which services limits to look for, and when you are building something new, you often do not know which part of your architecture will become the constraint. You find the ceiling when you reach it, not before. This is the gap that catches teams who have tested thoroughly, built carefully, and done everything correctly, and who discover on launch day that a number they never modeled is the number that defines their ceiling. What shifts when you understand this is not your relationship with cloud infrastructure. It is your model of what failure means. A limit failure is not the cloud breaking down. It is a designed boundary doing exactly what it was built to do. The infrastructure is running. A number was reached. That shift has a practical consequence. An outage caused by a limit has a different shape than an outage caused by a bug, a different diagnosis, a different resolution, a different timeline. The question is not what broke, because nothing broke. The question is what ceiling was reached and how to change it. The cloud is vast, but every vast space has walls somewhere. The question is not whether your application will eventually find them, it is whether you will know where they are before the moment it matters.